Hello, I'm Vladan Stojnic and I will present our work on label propagation for zero-shot classification with vision language models. This is joint work with Yanis Kalantidis and Yorgos Taulias. Standard zero-shot classification with VLMs assumes that we are given a list of class names and we want to perform classification of a test image. The class names are passed through a frozen VLM text encoder to produce class embeddings, while the test image is passed through a frozen VLM image encoder. Class and image embedding lie in a joint vector space where we can perform classification using a non-parametric classifier, such as comparing the image embedding and class embeddings using cosine similarity. The test image is then assigned to the class of the most similar text embedding. In this work, we assume that besides the list of class names, we also have access to a set of unlabeled images that we want to utilize to improve the zero-shot classification. These unlabeled images are passed through a VLM image encoder to obtain their embeddings, which lie in the same vector space as class and test image embeddings. We devise a novel non-parametric classifier that takes unlabeled images into account by leveraging geodesic similarities obtained by label propagation on the bimodal graph. We name the proposed method ZLAP for zero-shot label propagation. Let's have a look at how to construct the graph. A usual approach is to use a KNN search. However, because of a known modality gap where image and text similarities are not aligned, naive KNN search fails to connect nodes of different modalities. To solve this, we propose to perform KNN search separately per modality, searching first from image to image and then from image to text. This way, we enforce edges between modalities. However, because of the misalignment of similarities, we additionally propose to weight the edges that connect image and text modalities. Another question we need to answer is how to use a graph to make predictions for a new test image that is not part of the unlabeled set. We propose to represent a test image by its nearest neighbors from the graph. This way, we can obtain prediction for the test image by combining predictions of its neighbors. Additionally, we show that this way of representing a test image allows us to perform inference using label propagation in an efficient way. After we have a graph, we can look at how label propagation allows us to compute geodesic similarities. Label propagation is given by following iterative solution, where y is the encoding of query nodes, y hat contains geodesic similarities with respect to the query nodes, and S is normalized adjacency matrix. This iterative solution is intuitive and efficient to perform for sparse S. However, it is possible to show that this iterative solution is equivalent to solving the following linear system. One can then solve this linear system using the method of conjugate gradients, which is more efficient than using the iterative solution. Of course, this linear system has a following closed form solution, where L inverse is a matrix of geodesic similarities. However, considering that L inverse is a dense matrix, this solution is intractable for large graphs. Our label propagation typically uses equation 2, but we rely on equation 3 to enrich the intuition of the approach and also to propose a variant for speed-up inference. The technical details can be found in our paper. Finally, let's take a look at some of the results of our proposed method. First, we show that geodesic similarity aligns image and text better than standardly used cosine similarity. If we take a look at TSNE plot of image and text embeddings using a cosine similarity, we see that image and text embeddings are far from each other, with text embeddings being tightly clustered together. However, when we look at TSNE plot of image and text embeddings using geodesic similarity, we observe that images and text are closer together. Additionally, we show that ZLAP improves on top of CLIP and recently proposed InMap, both in the case of transductive inference, where we want to classify only the unlabeled images that are part of the graph, as well as in the case of inductive inference, where we want to classify new text examples that are not part of the unlabeled set. Combined with InMap, ZLAP obtains state-of-the-art performance across 14 commonly used datasets. Our paper and code are publicly available at the following links. Thank you.